Next session, next performance rockstar, it's going to be Taras. Taras is a part of Facebook. He is the organizer of the Performance Summit. So without waiting anymore, I will let you present.
Thank you so much for such a kind introduction, and also plug for the summit that I'm organizing. I think it's a great mission to actually deliver delightful experiences for our customers, because our customers demand not just fast but also meaningful experience on their applications, which oftentimes also means care about the footprint. And for the most part, in my talk, I am going to focus not so much even on the coding aspects, but on the things that allow us to build software for performance at the design phase. Because most of the time, unfortunately, we start thinking about performance only when things go bad, and that's usually too late. And sometimes, obviously, we don't want to prematurely optimize things, but by thinking carefully and taking advantage of the hardware that we have, we can just have a lot of advantages without too much investment. So today we're going to talk about the history and motivation of the append-only property. I'm also going to talk about a very controversial topic of why I believe that new storage is just a faster magnetic tape. Then we're going to see how this old pattern is powering modern applications. And I'm also going to touch a bit on the event sourcing and CQRS and how it leverages append-only principles. So let's start with a bit of history. And I believe I really like the way Jeff Bezos built a culture of his company around the things that are stable, that do not change. Because oftentimes in our industry, we tend to chase the next hot language, library, framework, or whatnot, in hopes that it's going to solve all of our problems. But as you probably noticed, they all change every single day. Even JVM is changing every half a year these days. So things are constantly changing, and oftentimes you cannot build successful, stable company around things that are so unstable. So maybe we should consider thinking about the things that do not change, and those are usually the things that have not changed in quite a while. That's actually, interestingly enough, a principle that is powering generational garbage collection, by the way, because we do believe that things that die, they die quickly, and things that do not die, they live for a long time, and they can be promoted to the survival space from the Eden. So I guess Bezos actually summarized it very well in his famous question of, instead of thinking about what's going to change in the next 10 years, I challenge everyone to think about what's not going to change in the next 10 years. And for Amazon, it's probably going to be something like people always want cheap stuff. They also want great customer experience and also fast delivery. And if we look back into the history of writing, we actually notice that most of the things that were written in the append-only way, because there was no way to erase things. You could only add things to your document, but never modify it. And the same principle was actually powering our accounting industry for quite some time, with an example of double entry accounting, which was used to avoid errors and also make sure that we have a very good record of everything that has happened. We can always audit it. We can check that nothing has been tampered with. And in practice, you probably noticed that mutation in general leads to a lot of complexities around data races, or synchronization on the distributed system level, where you have to coordinate multiple systems to make sure that everything is consistent. And for computing industry, I guess this was also the case with an introduction of magnetic tape in 1951. And obviously, in magnetic tapes, the pattern of access was usually append-only. You could just only write things, because obviously random access was extremely painful, highly undesirable. You would really not want to do any random access on a tape. So now I'm gonna claim that the new storage is just a faster tape. And if you look in the Wikipedia of the history of I/O, you could see a lot of different examples. So we have magnetic tapes, we have hard drives, then they got smaller, but then we got to SSDs, and then we've got NVMEs and all sorts of great stuff. And surely it's much better than what we had in the past, right? Like there is no way they have the same set of characteristics as, let's say, tapes. And I'm going to challenge that view. We usually tend to think that when we write things, we just use the write syscall, and then some magic happens in the kernel space, and things are written to the drive, and everything is great. But actually, there is so much complexity under the hood that is going on. There are tons of buffers. So, for example, a standard library would try to use buffers to make sure that you do not hit the disk at random locations all the time, just because it's very slow. So it tries to accumulate as much data as possible and then write it in a sequential way. And we're going to see later on why it's trying to do it in a sequential way. There are also kernel buffer caches that buffer even more things. And again, that's actually one of the things that people frequently forget about. They forget that system is really trying hard to not hit the storage device without the need, because it's very slow. And sometimes systems forget about fsync and whatnot, and tend to lose data if power goes down or whatnot. So to address the comparison of hard drives and SSD, you can see on this comparison diagram that even for SSD drives, sequential reads and sequential writes are more than an order of magnitude faster than random reads and random writes. Obviously, SSDs or NVMEs are way faster than hard drives, but they still have the same trade-off. Like you still pay for random accesses pretty heavily. So maybe we shouldn't use them. There are more benchmarks that show that sure, SSD are 5x faster than HDDs, and NVMe M2 drives are faster than SSDs and by 5x. But again, if you look at the comparison between sequential and random reads, you would see a huge difference between them. And why is that the case? Like for SSDs, like why does it happen? And for the most part, it happens because of the read and write amplifications. Everything that our storage operates on usually operates on some sort of blocks. And in the case of SSDs and NVMEs, those blocks can be 4K, they can be 16K, they can be even 4 megabytes. Like it totally depends on the storage. But basically, the idea is that you can only read and write in terms of these blocks. So, for example, if you're trying to modify even a single byte in a particular block, you have to, first of all, read that entire block, modify that change, and then write that block back. And so if your reads are random, it means that you're probably going to touch a bunch of different blocks, and that means that your writes are going to amplify into huge, potentially huge writes. And it also doesn't play very well with the garbage collection that happens on the controller level, because our SSDs, they don't necessarily want you to wait for all these reads to happen, so they would usually try to use new blocks, and also reduces the wear and tear of the drives. So not a great idea, basically, to do random reads and writes. And then you could say, well, okay, let's say for SSDs that's still the case, but surely that's not the case for memory. Like, memory doesn't really care about whether it's sequential or random, and you would be wrong. And there is again a huge difference between the speed you can get from the reading memory randomly or sequentially. And in this case, this is a logarithmic scale, but you could see that there is at least an order of magnitude difference between random and sequential memory reads. So why is that the case? And again, it's all about the mechanical sympathy. And I really like this quote by Jackie Stewart, who was a Formula One champion for a number of times. And he said that you don't have to be an engineer to be a racing driver, but you do have to have mechanical sympathy. And I think it's extremely relevant for engineering as well. And remember, I mentioned things about block structures in SSDs, and the exact same principle actually plays in the CPU world as well. So when you read the instructions, your assembly instructions on an Intel CPU, for example, what happens is that you actually read them in chunks. The chunk size depends on the CPU that you are lucky to use, but it could be either 16, 32, 64 bytes. It doesn't really matter. What matters is the fact that you have to fetch all these, all the instructions that are in that chunk, and then decode them and extract the data and execute them. So basically, it really matters a lot what kind of chunk you're going to get, like whether it's aligned, because if it's aligned well, what's going to happen is that it's very likely that you're going to get the instructions that are part of, let's say, a hot loop, and you wouldn't have to redecode them, because CPUs actually have a lot of optimizations. As you can see, there is a complex machinery even at the front end level, which includes things like a decoder stream buffer, which is essentially an extra cache that is used to cache the micro ops that are produced for the instructions, because, as you know, the Intel, for example, is a complex instruction. It operates on complex instructions, and those instructions are actually translated into micro ops that are more like a RISC-like, like reduced instructions that which are more efficient to execute and just simpler to execute. So again, it's extremely important to think about these building blocks that you operate on, because you can get a huge difference in terms of performance when leveraging it. And Bolt, for example, which is developed at Facebook, is leveraging code alignment extremely well to get huge performance wins based on the production profiling. And again, just by changing the layout of application so that things are read in the best possible way. So on the CPU level, the reason why you can have some pretty big wins from append-only or like, sequential consistent usage pattern is because you can use prefetching effectively. So you can guess, like in CPU there is a branch prediction and a lot of other machinery that allows you to predict what exactly you're going to need next, patch it before you need it, because most of the time CPUs are actually waiting for the data to operate on. They are not slow. Most of the time when you see some slowness, it's usually not because the CPU is slow. It's usually just because the way you access data is inefficient and CPU has to wait for your data. So distinguishing between the cases when your CPU is idle and waiting for data and actually busy doing work is extremely important. And you probably know that depending on how exactly you access your data in a matrix, for example, you can have an extremely different performance characteristics. Like if you can feed your data into the cache line, which is another block, you can think of it as another block, you can get massive performance wins. Then I guess another great example of why sequential accesses are so beneficial is because of the TLB, which is translation look-aside buffer, which is essentially a cache of the physical memory addresses that CPU machinery has to maintain to make sure that your virtual addresses are translated into physical memory addresses as efficiently as possible. And it's a very, very small cache. So you really want to make sure that you take advantage of it. But if you access your memory in random patterns, it's very likely that you're not gonna leverage that cache very effectively. You're gonna have a lot of misses, and you're gonna have your CPU waiting for data for more than necessary. Also, sequential accesses give you advantages of using direct memory access or even remote direct memory access that allows you to essentially map address spaces between different machines and transfer data without any CPU involvement, which is great. Then another great pattern that you can get from sequential access is zero copying. So usually what happens is that when you try to transmit data between, let's say, your two applications, you have to involve the kernel, which usually has to copy data from user space into the kernel space. Then it has to copy from the kernel space into the user space of the other app. So a lot of copying, which is completely unnecessary. And there are APIs like SendFile that allow you to perform direct transmissions via direct memory access or whatnot. But most of these techniques, they rely on the fact that you have a sequential memory space that you're operating on. And now we are actually on the most exciting part, like what are the modern applications of this pattern? And it's used pretty much everywhere, but you can, I guess from the question, like, what is the common thing between Disruptor, Aeron, Kafka, Raft, InfluxDB, IOU-Ring, and all these things? They all leverage append-only data structures or approaches to get maximum performance. And how it's done is in many ways determined by the use cases. But for example, InfluxDB is heavily leveraging compression to avoid the amount of data that you have to read from memory and write to memory. And the fact that when you store your data in a sequential way, it's actually very easy for you to use a lot of interesting encoding techniques like delta encoding, where you, especially which is like super convenient for time series databases, which is InfluxDB is meant for. But that allows you to essentially store the difference between different sequential copies of data. And then you can even use another encoding techniques like run-length encoding to get it to even smaller values. And I cannot overstress, I guess, the importance of reducing the size of the data you have. It's oftentimes much more beneficial to spend a few more cycles on the CPU decoding and encoding the data than transferring the data because memory access is slow. I/O ring, which is powering the new generation of Linux kernel asynchronous request, is also powered by the essentially append-only data structure that is implementing the circular buffer. And what it allows you to do is you essentially don't have to have any blocking. You can map the space between the kernel and the user space, and then you can use a simple atomic instructions to bump your tail and head of the ring buffers to make sure that there is no need for expensive coordination, and there is also no need for copying. That's actually the reason why I absolutely recommend everyone to take advantage of I/O ring whenever possible. It's way, way faster than AIO or any other mechanisms that you may have used in Linux previously. Then Append-only is powering pretty much all the databases that you can think of, because all of them are using transaction lock. Pretty much all of them. I don't know. And also file systems are mostly using journaling systems, and journals are usually append-only. Why? Because it's really fast. So there is no excuse not to use it. Then there is an amazing technology developed by Martin Thompson at LMAX and a few other of his colleagues that is also pretty much powered by the append-only data structure, which is it's also technically a circular ring buffer, but it has some interesting extra additions of having different buffers, like there is a clean, dirty, and active one, which are swapped by the thread that is unable to write new packets. So again, zero copying, no blocking. In fact, it's actually wait-free, not even lock-free. And wait-free guarantees that your threads are going to make progress in a bounded time, which is the strongest and the most desirable property you can ever get from your algorithm. So again, extremely powerful pattern and concept, and you should totally embrace it. Simple binary encoding. Again, super awesome technique that allows you to avoid copying, just because you can write things in the append-only way and also use something like a flyweight pattern where you essentially just cast your memory space into some struct and access it without having to copy anything or mutate anything. And it's very easy to get the length and whatnot way. You can also use append-only mechanisms and ring buffers to do smart batching. So instead of having contended access to any shared resource like your I/O device, you can just use wait-free ring buffer for all the writes, and then you have a single thread that reads all the elements from the queue and pushes them in an efficient, uncontended way to the I/O device or any shared resource that you have. It's also powering Disruptor, which is an extremely popular pattern and implementation of the ring buffer in Java world. Again, it was developed for LMAX. And you can see that the mean latency is multiple orders of magnitude lower than what you get from array blocking queue in Java, for example. Again, mechanical sympathy, append-only, zero copying, and append-only property. Another interesting data structure is the C buffer. So for the cases where you absolutely have to have contiguous virtual space that you have to map, you can actually map the same virtual space multiple times into a different location so that it's easier to use it for DMA, for example. Again, append-only is totally cool for it. Beep buffer is another idea that also implements the similar idea of having a contiguous virtual space, but it doesn't actually require you to do shenanigans with the mmap, like in the previous example of C buffer. You just use multiple regions for your ring buffer. Highly recommend checking it out if you have to deal with DMA. Then another awesome data structure is the log structured merge trees that is powering super fast storage devices. Like you probably heard about the big table from Google. You probably heard about LevelDB or RocksDB, Cassandra, HBase, and many other systems. They are all powered by the log structured merge trees that are heavily leveraging the append-only data structures because we accumulate data in memory in M tables, and then we write them in a sequential way to assorted append-only files that are never mutated, and then you merge them on multiple levels to compact them and also make sure that they are smaller. But again, super powerful idea powering modern workloads. The cool thing about the append-only is that it's not just for LSM trees. Apparently, B trees can also be implemented with append-only approach, where you represent, if you represent your tree as sequentially written branches and then the metadata node that points to all the nodes that were written previously, what you can do is you can actually think of it as a persistent data structure that allows you to modify a tree by creating a new root and updating all the nodes on the path of the mutation. So what happens is that you actually have all the history of the entire tree if you need to access it. So you get the multi-version concurrency for free, and then you can do garbage collection if necessary to remove the things that you no longer need. But you can see that it's extremely powerful technique because it can allow you to have many readers, many mutations at the same time without any conflicts. You always have consistent view of your world and super fast writes, because you don't even need to have a transaction log, because what you write things in append-only, so the writes happen so quickly that you don't even have to have a journaling. You get it for free. Then we finally got to the event sourcing, and the idea is that it's much faster to write things in append-only. So you potentially separate your writes from reads, and your reads are just some sort of materialization, like materialized view of the query that your users want. And so this way you can optimize your reads and you can optimize your writes separately, because usually you cannot do you cannot optimize both at the same time, because if you usually when you want to optimize reads, you would either have to have some sort of indices or whatnot, and they all require you to perform extra computations and extra writes, and that's expensive. So by separating the writes into the append-only storage and reads into sequentially queryable storages, you get the best of both worlds. And you essentially use something like a double entry bookkeeping that I mentioned at the beginning, where you store all the events that happened to your system, and then you can replay them, which is especially extremely useful when you have some sort of bug. So you can fix the bug, replay all the events that happened since the introduction of the bug, and get the new correct view of the world. So why do I think you need to use append-only? Because you can get log-free algorithms in most of the cases. Like, for example, I mentioned the ring buffers. I mentioned B-trees implemented with append-only. They do not require expensive coordination or locks. You can achieve zero copying semantics with IO ring and other algorithms. You can leverage prefetching effectively. You can leverage it on many levels. For example, you can use fadvise or whatnot in Linux to tell the kernel that, oh, I'm actually going to be reading a lot of data in a sequential way. So the kernel itself will try to prefetch as much data as possible so that when you need it, you actually already have it in cache for you, super fast. Branch prediction. By accessing your things in a sequential way, you increase chances of CPU preloading things into the cache before you even need it. Super fast, super great. Single writer pattern, which is the concept that I touched on with the smart batching, that allows you to reduce contention on the shared resource and also get the data race-free semantics. You can reduce wear and tear, and that's actually one of the reasons why we often have to build customized storage engines instead of using something like SQLite or whatnot, because even though SQLite is extremely capable and convenient to use and pretty much available everywhere, the problem with it is that it has to operate on random patterns, which usually results in unnecessary wear and tear of the flash drives on the phones especially, which is a big problem. You can get effective compression, and as I mentioned, you can use delta encoding and many other techniques with sequentially written and read data. And a lot of the technologies like JVM JIT, for example, is able to take advantage of the sequential pattern optimization, where things like lists, array lists, or actually not even array lists, but even something like linked list can be at runtime optimized into something that is essentially like an array by seeing that, okay, you are accessing this in a sequential way all the time, so let me just, during garbage collection, restructure the memory in such a way that all the nodes are actually sequential, because this way you get the benefits of TLB, of caching, and everything I mentioned previously. So the takeaways: prefetch and use speculative execution whenever possible. Keep in mind that everything under the hood is in blocks. So think about how you can pack as much useful stuff into that block as possible, but also don't forget about the false sharing, which can bite you if you improperly pack things that should not be packed together. Use flyweight pattern with zero copying to get super fast performance, reduce garbage collection overhead, and other downsides of managed runtimes. Compress your data. CPUs are super fast, so don't make them wait for your data. Avoid locks. Using single writer design and lock-free data structures, you can significantly speed things up, but also get much more predictability, because every time you get locks involved, there are potential for deadlocks, and just in general, you are at the mercy of the runtime or kernel of how things are going to be scheduled. So you cannot expect your system to be real-time. Avoid branches or make them predictable. So you've probably seen examples of loops that operate on the sorted data, and you get huge benefits from sorting data before you actually operate on it. Even though you technically don't need sorted data, branch prediction makes a huge difference. Again, think about CPU as being idle most of the time. You try to feed it as much as possible. And then, on a related note, sometimes the algorithms like insertion sort are the best way to go, because interestingly, insertion sort has one of the most predictable access patterns. So it plays extremely well with branch prediction. And for small data sets, it works like a charm. That's actually the reason why it's powering most of the hybrid algorithms in modern software. Things like intro sort or team sort or many other algorithms usually have at the base of their recursion, they end up using insertion sort to speed things up. And that's pretty much it. So it's time for questions.
And there are a couple of things that I was aware of. The others I didn't heard about. So I was googling, find some couple of articles. So I made some notes. So I have to make some readings after, to be honest. So thanks for bringing that up. At least there's a couple of things for Java, because I'm mainly dealing with Java here. So it brings my interest. So I have to make some homework. So as of now, I need to read to ask you more questions, to be honest, from my end. But yeah, thanks, because it makes completely sense what you just mentioned. Yeah, having the data more accessible, avoiding deadlocks and all stuff like this. So thanks for bringing that up. I think that will be very useful for us.
Thank you for the opportunity. I realized that I had to rush through a bunch of things just because this is such a simple thing, but it is just such a vast topic because it pretty much covers everything these days. So that's why I had to pack, I guess, way too much stuff, and it still doesn't cover even a third what I had in mind before this. So thank you for the opportunity to present this pattern. I hope it's going to help someone to build faster and more reliable software.
I'm just wondering, in your experience, like when you begin working with projects, how often do you have to school the developer on how to take advantage of these types of efficiencies? Because it seems like you could gain a lot if you just had this knowledge available to you.
Yeah, obviously, I believe that it's like the more you know, the better you can take advantage of the system. But what we try to obviously do is to just make sure that the systems that we build, they are powered by these technologies and provide the benefits for most of the use cases for free. So just by virtue of, let's say, using something like RocksDB or, I don't know, like InfluxDB or whatnot, you're going to get a lot of benefits. So you don't have to, like, ideally, you don't have to understand all these things on a daily basis, but you can get huge wins from leveraging them. And the idea itself is actually fairly simple. Like, just try to access your data in a predictable way. Even if it's not linear, but at least predictable. Like do not read random data at random parts, or do not copy data unnecessarily. And we do have, I guess, some attempts to scale the knowledge by using static analysis tools. In fact, I don't know if you've heard, but we do have like Infer, which is the static analysis, which, by the way, works for Java very well as well. So it has even things like complexity analysis, which allows you to analyze complexity of your function before and after your change. And let's say if you go from linear to n log n or quadratic, it's going to actually flag it and tell you, oh, you're using, you're increasing complexity of your algorithm. Which is pretty cool, but unfortunately we don't have anything like, oh, you're using inefficient way of accessing data. And I believe that this is going to be the next big thing where we are able to actually detect these patterns in code and communicate them effectively to developers. That's actually the reason why I'm very excited about the efforts like Amazon Code Guru, for example, that on top of using production profiling to get the dynamic data from the real use cases that you have, it generates meaningful and actionable suggestions of how to modify your code to take advantage of the patterns that correlate with high performance. And I believe that this is probably the future, like where we can see in production, in using production profiling, we can definitely see that the data that we are accessing follows this pattern, but your code is not taking advantage of it. So maybe you should restructure your code to do this. So I don't think it's possible to scale this knowledge without automation. So we need to leverage static analysis with production profiling to educate our users in a very helpful way. We don't want to just, like, oh, you regressed performance, good luck dealing with it. We should have a very guided experience where we are able to educate people. It's like, when you mentioned that, like, you have to go to school or whatnot, or that you didn't understand something from my talk, it's actually like the way I hear it, it's like I failed because I'm a huge fan of Richard Feynman, and he was a believer that if you cannot explain your concept to an old lady that has no physical background in physics, then you just don't understand the topic well enough. I'm gonna use an excuse that I just didn't have enough time to explain it in enough details. But it's a lame excuse, and I would actually love to go much deeper into any of the concepts that I covered. So we obviously don't have as much time to spend on an individual basis with every single developer to make sure that, oh, did you know that your CPU is operating similarly to your kernel and your software stack? It's actually like, it's all very similar. There is a unifying underlying theme that spans across all of them. And so it's not actually a whole lot that you need to learn. But the more examples you experience throughout your career, the more you realize this. Because just a dry theory does not help much. Like, you really want to experience it in practice. You really want to see the impact of append-only storage that we have built, purpose-built, for example, for our, like when I worked on Android, there was a platform called Android Fitness, and we built custom storage instead of SQLite, and it was multiple orders faster than SQLite, even though we wrote it in just like a week or something like that, and that includes all the testing and tuning and everything. So it was very, very easy to write, very, very easy to reason about, and multiple orders of magnitude of wins. When you experience this stuff, you're like, holy moly, I'm gonna use this pattern everywhere. Otherwise, it's just a dry theory.
Sure. So thanks and welcome to the PAC community. We always are happy to have a new PAC members with us. So it's great. So
Yeah.
Thank you.
Thank you so much for the opportunity. It's been an honor and pleasure to join the PAC community. I'm looking forward to learning more from the community, and feel free to ask me any questions if you would like to dig deeper into any of the topics. I'm super passionate about it. So yeah, thank you so much, and thank you for organizing this awesome event. It's been a pleasure.